All right, now we're going to take a look at polymer classification by reaction type. Before, we classified polymers according to their construction, whether they were block polymers or copolymers or homopolymers, raft copolymers, etc. And now we're going to actually look at how the monomers are put together to make these polymers. So look up here with me. It says addition polymers. Addition reactions involving pi bonds includes cationic addition. So you can imagine that's got something to do with cations, anionic addition, and then free radical addition. Free radical addition occurs through a chain reaction. So we're going to start with this. We're going to start with free radicals, and then we'll look at anionic mechanisms after that. Just like we saw way back in chapter 10 of Organic Chemistry 1, when we discussed radicals, when we make a polymer via radical addition, it's going to occur via initiation, propagation, and termination. So if you don't remember what those terms mean, let's review. Initiation is where we start with something that doesn't have a radical and we make a radical from that. So there's actually kind of two initiation steps. The first one is where we throw in our radical initiator. If you remember the anti-Markov-Nikov addition of HBr across a double bond using HBr and ROOR, or an organic peroxide, if you remember what this was for, okay, this substance right here is to make a radical. So when you treat that with heat, it breaks homolytically to produce two radicals. So now you have a radical in your solution, and that radical, that oxygen radical, can react with one of your monomers, which is going to be an ethylene derivative. And check out these three arrows. You end up making a bond between the oxygen and the carbon here, and then you end up with a radical. Well, now that you have a radical, if you subject that to another molecule of the monomer, then you're going to get another radical addition like this to form a new radical like that. I guess that wasn't a proper arrow. Let me fix that. There we go. Like that. And that's what we see here in the propagation steps. If you remember, propagation is where we start with a radical and then we end up with a radical. So we're going to keep adding monomers to that initial radical. And then once you keep adding them, then you keep forming radicals, and it keeps adding and adding and adding. So we make the chain longer and longer and longer. And then what's termination? Well, again, if you remember from chapter 10, termination was when any two radicals meet to annihilate a radical. Okay, so let's see here. It could be the end of the polymer reacting with an oxygen radical that was formed up here. It could be two of the ends coming together like that. But either way, termination is nothing more than two radicals coming together. So again, initiation, propagation, and termination. And this is how you grow a radical by, how you grow a polymer by free radical addition. Next, we're going to take a look at a couple of ionic mechanisms that can be used to assemble polymers. And we're going to start with cationic polymerization. So you can imagine this has something to do with a cation. It says here that monomers for addition reactions are derivatives of ethylene. So that means that we've got some kind of ethylene, and then we could have an R group on it, or maybe two R groups on it. We're going to see that in this section, that we're going to usually just have one R group on our ethylene derivative. However, when we're making a cationic polymerization process, it's going to work well if the monomer contains an electron donating group. So this R group here has to be an electron donating group. And you can probably guess, even if you haven't looked at the next slide, that why is an electron donating group a good thing if your cation is going to be an intermediate? Because electron donating groups donate electron density into the cation to stabilize it. Right? If you think about, going back to carbocation stability, if you compare the carbocation stability of a secondary carbocation versus a tertiary carbocation, well, the tertiary is more stable because these R groups donate a little bit of electron density via hyperconjugation. So anyhow, let's move on from there. And let's take a look at some examples of electron donating groups. First of all, just any kind of alkyl group, like a methyl group. Again, that donates electron density via hyperconjugation. If you have an ether, the same thing, and you could even practice drawing the resonance structure that shows that this can donate electron density. Oxygen has those lone pairs on there. And the same thing if you have an amine. You could also draw a resonance structure that shows that you can donate this pair of electrons, and I'll let you try to draw that resonance structure on your own. So without further ado, let's take a look at the mechanism. The first step is going to be the initiation. It's not a radical initiation, it's initiating the formation of a carbocation. And the way that we do that initiation is by treating our ethylene derivative with an acid. So you see that this double bond in our monomer behaves as a base, or a proton acceptor, and we end up forming the conjugate base, but we form a carbocation. So here you see why that electron donating group is a good thing, because it stabilizes that carbocation. Now, in terms of the acid that's used, what are the acids that come up the most in organic chemistry? Things like HCl, H2SO4. However, we don't use those kinds of strong acids for initiating a radical reaction. Usually the acid that is used, and our book doesn't go into much detail about this, so don't worry about piles and piles of detail, but it's usually an acid that's made from a complex between boron trifluoride, so BF3. Maybe I'll write out the whole Lewis structure here. So if you have BF3, which is a Lewis acid, it's an electron acceptor, and water, what happens is that the water donates a pair of electrons into this empty p orbital, and you end up with this complex that looks like this. So let me just scribble the whole thing in here. So you end up with this Zwitter ion like this. Oops, it's not a very good. There we go. But this is what would donate the proton. So you would donate a proton from this as your acid. It's not a strong acid, but it's strong enough to initiate the reaction. This mixture of BF3 with water. So we can put here BF3 and H2O together. All right. Anyhow, so once you've made that carbocation, then you can imagine that your next monomer is going to behave as a base. It's going to attack that carbocation, but then you produce another carbocation, and so on and so forth until you build up your polymer through these cationic intermediates. Then for termination, there's a couple of possibilities. You could either rip off a proton using a base, so you treat it with a strong base that rips a proton off of it to do an elimination and forms a double bond. So that's one way to end the polymer. Or if you throw in an appropriate nucleophile that can attack the carbocation, then that can also terminate the whole process like that. So that's cationic addition. The take-home message that you need as a student are these two mechanisms, the fact that you need an electron donating group, and then how to terminate it. Okay, those are the things that you really need to know as a Chemistry 3111 student. Now, in terms of, what kind of R groups can we have on here? Well, if we're proceeding through a cation, the same rules for carbocations always apply. Thus, you can imagine if you had isobutylene, it's kind of cut off here, isn't it? If you had isobutylene as your monomer, right, there's nothing wrong with using that, because once it gets protonated, you get a tertiary carbocation, and that's perfectly stable. This on the top here, this is totally reasonable. However, cationic polymerization is not going to work if we're using ethylene. Why doesn't that work? It's a nice idea, but it can't work because you end up with a primary carbocation as an intermediate. And what do we know about that in organic chemistry? A primary carbocation is very unstable. It's a big no-no in organic chemistry. All right, so if we're not going to form it, it's not going to work. You've got to use something else to polymerize ethylene. All right, so that covers cationic addition. We're going to look at some practice problems in a little bit, but let's cover one more type of addition polymer, the last kind. We've covered radicals, we've covered cationic polymerization, and now we're going to talk about anionic polymerization. And just like the cationic polymerization required an ethylene derivative with an electron donating our group, now for doing anionic polymerization, we require an ethylene derivative with an electron withdrawing group. Why? Because we're going to be forming, intermediates where we have a negative charge or a carbanion here. So you need something that's electron withdrawing to stabilize that. What are some examples of electron withdrawing groups? These came up a lot in the chapter on electrophilic aromatic substitution. Things like a nitro group or a nitrile or anything that's got a carbonyl directly attached to it, right? We know that has a dipole going this way. So again, those would be considered electron withdrawing groups, which again are necessary in order for anionic polymerization to occur. Let's take a look at the mechanism. It's the same three phases: initiation, propagation, and termination, but the initiation is not going to be initiated by an acid. It's going to be initiated by a nucleophile, and the nucleophile that we like to use is butyllithium. So it says here, initiated by a highly reactive anion. So we like to use butyl lithium, right? And the Lewis structure, or the charges are the butyl is the anion, and the lithium obviously is the cation. It's a group 1 metal. So the butyl anion attacks the ethylene derivative, and then we make a carbanion. But again, now we've got an electron withdrawing group on this, so it pulls electron density away, further stabilizing it. Now that you've made your carbanion, you can imagine that it just does a nucleophilic attack after nucleophilic attack after nucleophilic attack, just like that. So we keep adding to the polymer and adding and adding and adding. And in order to terminate it, we have to throw in some kind of, something that's going to react with that negative charge on the end in order to get the polymer to stop growing. So you could add water as a proton source, or carbon dioxide, some kind of, weak acid, or electrophile. And we actually call this, a living polymer when you can keep adding monomers to it and it keeps growing and growing. And let me just give you a little bit more information here. The anionic polymerization, I was going to bring it up on the last slide, but I knew I had it on here. You probably noticed that it's a Michael addition, right? If you're adding this carbanion on this carbon of the double bond, that's a Michael donor and a Michael acceptor. So anionic polymerization is nothing more than an analog of a Michael reaction. It's really all it is. And that electron withdrawing group, because it stabilizes the intermediate, the anionic intermediate, like let's say you add this monomer and then this one, and then it's just kind of stuck hanging out here. Well, this thing is so stabilized by this where's my red pen? This thing is so stabilized by this electron withdrawing group that it can just sit there. Okay, it can just sit there in the reaction flask, and then you throw another monomer, like it'll just stop reacting. Then you throw another monomer in there, like this, and then it's going to react like that. And so we call this a living polymer. Living in the real world, right? A living polymer. That's what we call it, because you can just keep adding and then it grows, and then you add and then it grows, and then you can stop the reaction when you want. All right, so anionic polymerization. Now that we've covered radical polymerization, cationic polymerization, and anionic polymerization, let me show you a couple other types of interesting ways of making polymers just by using other chemistry that we've seen all through organic chemistry, mostly organic chemistry too. But check this out. Everybody who's hearing the sound of my voice, whether it's live or watching it on YouTube, knows what a Fissure esterification reaction is, right? This is one of the most important reactions that we learn in organic chemistry too, is when we take a carboxylic acid, we combine it with an alcohol, we use an acid catalyst, and we remove water. Normally in the carboxylic acids chapter, we just wrote minus H2O. They're showing it as a product over here. That's fine. But we end up forming an ester. So let's imagine, how could you harness the power of Fissure esterification? Pretty easy chemistry to do. How could you harness this to make a polymer? Well, what if you had some kind of molecule? I'll just draw a sphere like this. What if you had a molecule that had a carboxyl group on each side, on each end? And then what if you had some kind of alcohol that had a hydroxyl on each end? Right? Then you could form a bond here, and then this hydroxyl is going to be open to react with the next molecule of acid that's next to it. So you'd have another one. Where's my black pen? Here we go. You'd have another molecule of the diacid, like this, like that, and then you'd form a bond here, and then where's my highlighter? You'd form a bond here, and then it just keeps adding and adding. So you're basically doing nothing but a bunch of Fissure esterifications to make a poly what? ester, because you're making a bunch of ester bonds. And I'm sure you've all heard of polyesters. I know you have. But that's how a polyester is made. Nothing more than that. Just a bunch of Fissure esterifications. Here's a specific example. This is the synthesis of a polymer called polyethylene terephthalate. So it's made from terephthalic acid, this acid here, and ethylene glycol, which is a major component found in antifreeze. And you see what's going on here is that you have this hydroxyl reacting with this, or sorry, this carboxyl reacting with this hydroxyl. You lose water, okay? And then you form an ester bond right here. And then it keeps doing it over and over and over. So we have an ester bond here, we have one here, we have one here, and so on and so forth. And that is how we make a condensation polymer. And this is the synthesis of a polyester. Why? Because it's ester after ester after ester. So now you know how to make a polyester, and then you can harness that power to make like a leisure suit or something. All right, so a polyester. The next one is the synthesis of nylon. And if you've ever wondered, like, what is nylon exactly? Well, everybody here knows what an amide is. I know you all know what an amide is. You know, we've looked at them many times. We just looked at amino acids. So an amide is where we have a carbonyl, and then we have a nitrogen attached to it, and we might have another R group like this. But a nylon is nothing more than a polyamide. That's all it is. You have amide after amide after amide. There are many types, or there's several types of nylon out there. There's not just one nylon, okay? A very common type of nylon is called nylon 6,6. So nylon 6,6 is made from adipic acid, which has 6 carbons in it, right? 1, 2, 3, 4, 5, 6. And then 1,6-hexane diamine, which hexane, you know, has 6 carbons. So 1, 2, 3, 4, 5, 6. So that's why we call it nylon 6,6, 2 carbons in each molecule. And again, you see that there's an amide bond here, there's one here, there's one here, and so on and so forth. So there you have it, my friends. Pretty neat. The repeating unit of the nylon 6,6, if you look very carefully, the repeating unit would be, you know, kind of starting here and then ending around here. Yeah, something like that. That would be, if you put an N there, I'm just going to write that in because this is going to be relevant in a little bit when we do a practice problem. So repeating unit of nylon 6,6. Give me a thumbs up if you follow me on the idea of a polyester and a polyamide, which is a nylon. And there's several different types of nylons out there. What else are we going to look at? A polymer like Lexan or something like that. If you've ever heard of a polycarbonate, polycarbonates have all kinds of uses. If you own a Nalgene bottle, so those big 1 liter bottles that students like to bring to class sometimes, or you use them for camping and things, those are made from a polycarbonate. And polycarbonates just involve repeating units of carbonates. And if you're like, what the heck's a carbonate, Mr. Dion? Well, a carbonate is a new functional group. It's the last functional group you're going to learn in this class. However, hopefully you remember the carbonate ion from Gen Chem, well, from Gen Chem 1, 2, organic 1, 2. The carbonate ion is CO3 2 minus. So, you know, the Lewis structure of carbonate is, you know, you've got a carbon with a double bond, and then you've got 2 bonds to oxygens with minus charges. So if you get rid of those negative charges, and then you put 2 R groups on the oxygens like that, that's an organic carbonate. So there you go. I think it's your last functional group that you'll learn in organic chemistry is the carbonate. So it's a polycarbonate. And how do you make a polycarbonate? Well, it can be made from phosgene. Phosgene is always kind of a funny compound because it's got no phosphorus in it. It kind of sounds like it does, but it doesn't. Anyhow, phosgene is like the dichloro analog of formaldehyde, right? You take formaldehyde, you replace both the hydrogens with chlorines, but you can imagine that this thing is a wicked powerful electrophile. You've got a dipole going this way and this way and this way, and that's why phosgene was used as a what's the word I'm looking for? Is a chemical warfare agent because it's such a powerful electrophile. It can react with biomolecules in your body, and that's not good. So anyhow, let's not go into the details of that. But you can imagine that if you have, you know, 2 molecules of an alcohol, like this, that's going to attack this like nobody's business, right? To make a tetrahedral intermediate, you lose chlorine, it does it again, and you end up forming a carbonate and some HCl along the way. And that's how polycarbonates are made. So what I was kind of getting ahead of myself on was this idea right here. This is the synthesis of Lexan. And Lexan is what's found in Nalgene bottles. And you might have heard of the Nalgene bottle controversy, which is where there's, different reports about the detrimental effects of bisphenol A, this compound here. I'm not going to go into, any opinions that I have on it, but you could do some research on it. In fact, if you go to a store like REI or something, you'll see Nalgene bottles and it'll say on it, bisphenol A, which is BPA, it'll say BPA free on it. So if you want to do some research on bisphenol A, you might find that interesting. But the reaction between bisphenol A, which is a diol, right? It's a bisphenol, and phosgene produces this compound, Lexan, which is very, very strong, not super expensive. I think it's even used in, windows that, let's say you have a windshield in a dump truck in a quarry or something like that, those giant dump trucks. I think oftentimes those windshields are made out of Lexan because it's just so strong and they get hit with rocks so much. I know the windows in some fishing vessels are made from that because they get hit with such strong waves. Anyhow, something kind of interesting there. So a polycarbonate Lexan would be one of those. Well, that's a lot of information about ways that we can classify polymers. So we've looked at radicals, cations, anions, Fissure esterification to make a polyester. We looked at amide synthesis to make a nylon, and polycarbonates, which can be made from a diol, and phosgene. So this question simply asks us, determine whether the prep for any of these polymers would be best achieved using cationic addition or anionic addition. Now let's review. Cationic addition is where we had some kind of cationic intermediate. So we would want to have an electron donating group because that would stabilize the cation. And anionic addition is where we had an anion as an intermediate. So we would want some kind of electron withdrawing group. If we go to A, we have a bunch of nitriles on here. Anybody suggest, would you want to make A via cationic addition or anionic addition?
Anionic.
Absolutely. Yep, anionic. Because a nitrile is strongly electron withdrawing. Couldn't agree more. I'll even scribble up here EWG. What about the next one? What do you think about that one? You've got a methoxy group on it. Methoxy, you can kind of think of it in two ways because the oxygen is electron. Go ahead.
Cationic.
Yeah, it's cationic, absolutely. Right, and that one's tricky because, an oxygen is electron withdrawing. I mean, it's the second most electron negative element in the periodic table. However, the methyl ether is considered to be electron donating, isn't it? Why? Because that lone pair, one of the lone pairs on here, can go in here and stabilize that positive charge. So now you've got something that's, with enhanced stability like that. So yeah, anyhow, let me put a little tail on that. There we go. So cationic, because this is an electron donating group, so we'll put EDG. And then the last one, we have some methyl groups. Those are also called alkyl groups. We know they're electron donating via hyperconjugation. So these are also electron donating groups. So we'll put cationic on this one as well. All right, there we go. So cationic and anionic polymer. Next one says, draw the polymer that you would make from the acid catalyzed reaction between oxalic acid and resorcinol. Resorcinol is a diol and oxalic acid is a diacid. So we're going to use Fissure esterification. So Fissure esterification, which is the formation of an ester. So, I mean, we can start anywhere we want, really. And it just says draw the polymer is all it's asking us to do. I'm going to start kind of on this carbon here, just thinking of oxalic acid. So I'm going to start with a carbonyl like this, and I'm going to put an open bracket here and start from there, okay? So I've got my first carbonyl, my second carbonyl, and then I'm going to have an oxygen. And then I'm going to have, right, this is my ester bond that I'm forming. Okay, so now I have to draw the resorcinol molecule around that. So I put in my aromatic ring like that. Then I have another hydroxyl coming off of here, but that's going to form another ester with oxalic acid. So let's pencil that in. So we're going to have an ester going down here. And we've got a carbonyl coming up. Then we've got another ester. We've got another ester coming here. I don't know where I'm ending with this. I'm kind of going on a little too long here, but whatever. It's kind of fun doodling it, I guess. So we could put another one and so on and so forth. But that would be the repeating unit would be something like that. I put 2 repeating units in there, but that would be it. Maybe I could clean this up a little bit here. There we go. Why don't we do it? Oops, that's not good. We do it like this and like this. There we go. Something like that. Give me a thumbs up if you think you could draw that. Just a repeating unit here, and this would again be a polyester. Polyester. So just from this little problem, you can see like how many different types of polyesters you can draw. So again, this kind of shows you why polymers is at the cutting edge of research, because people are making different kinds of polyesters every day and investigating the properties of them and trying to exploit them to make, it could be anything. It could be flame retardant materials. It could be, something for a prosthetic, any kind of thing that you can think of, really. Let's see. Kevlar is a condensation polymer used in the manufacture of bulletproof vests. We'll put here and canoes. So lightweight and strong canoes. We're going to identify the monomers that you would use in the preparation of Kevlar. So we see that the types of bonds here that we could use to link these together are amide bonds. There's an amide bond here. There's an amide bond here, here. So we can see what the repeating units are here. We have this diamine. Let me get a pen here. We have this diamine, which looks like this. Then we have a diacid that's going to come from here. Then we have the diamine again. It's the same old one. It's just kind of showing you 2 repeating units like that. So our amine is going to look like this. We've got our aromatic ring. So you could give this a bunch of different names. You could call it para. You could call it para amino aniline, I guess. That's one name you could give it. I don't think that's the proper name. It would be paraphenylene diamine, which is neither here nor there. Does it say name them? No, it just says draw them. But anyhow, the name of this one would be paraphenylene diamine. And I would never ask you to just come up with a name like that off the top of your head. If you called it, something like para amino aniline, I would totally accept that. And the next one is the diacid, which looks like this. So we've got a carboxyl group on this side, and we've got a carboxyl group on this side. This is called terephthalic acid. I think it came up earlier today. So terephthalic acid. Pretty neat. Kevlar. It's got all kinds of, and you can imagine what makes Kevlar so strong is if you were to repeat this whole thing and then move it up here, there's so much opportunity for hydrogen bonding between these things, and then if you have an NH, if you had an NH here, then there's so much opportunity for hydrogen bonding. So that's what imparts some of the strength to Kevlar. Very interesting material. Let's try another one. This question says, identify the monomers that you'd need to make each of the following condensation polymers. And the next question, the very last one, is about nylon 6. Let's check this out before we go back to this one. It says, nylon 6 is a polyamide used in the manufacture of ropes. It can be prepared by a hydrolysis of epsilon caprolactam to form epsilon aminocaproic acid, followed by acid catalyzed polymerization. So they basically take this molecule and break it apart to make this thing, and then you can make something called nylon 6. Okay, it says draw the structure of nylon 6 and then compare the structure of nylon 6 with nylon 6,6 that we looked at just a while ago. And then it says which polymer exhibits a smaller repeating unit. So what I'd like everybody to do is we're going to take a short break. I'd like everybody to try 27.14 A and B. Just see if you can come up with the monomers that were used to make these condensation polymers. They even specifically tell you they're condensation polymers. Then I'd like you to try to draw nylon 6 and then compare it to nylon 6,6 and see if you can figure out which one is a smaller repeating unit. All right, smaller repeating unit of the two.